So I would like first to thank IMSC and especially Shanoli for the hospitality and hosting me here. Maybe I'm going to start by a simple example. So you look at the polynomial equation. And this polynomial actually has a Galois group, which is isomorphic to S3. And the symmetric group on 3 letters. So you have that on the one hand. And on the other hand, you have the following Q expansion product and you can certainly, you see it's a Ramanujan type Q expansion, and you can expand it let's say. In the following way. And what is the connection between those two objects? It's the following connection. And so, for p prime number, consider the number of solutions mod p, and there are 3 possibilities. And now consider AP, and you can compare those 2 things. So there are three possibilities. There could be 0, 1, or 3 solutions to this. So if there are 0 solutions, there could be 1 solution, and there could be 3 solutions. And so you can do that for every prime number p. And on the other hand, you can look at the corresponding value of AP, and there is indeed a correspondence. So when there are 0 solutions, you have AP is equal to 1. When there is 1 solution, you have AP equal to 0. And when you have 3 solutions, you have AP equal to 2. Okay, so it's sort of an amazing coincidence. So if you expand this, it gives you the number of solutions of this equation mod p, at least the p is coefficient. Of course, this is part of a general pattern. And okay, p shall not be equal to 23, which is a bit special in that case. Okay, so the Harris-Venkatesh conjecture is about something more subtle even than this correspondence that comes out of both this equation and a Q expansion like this. So first, let me now explain the context of this correspondence. So on the one hand, you consider rho a Galois representation and I put certain condition on this. Okay, so this is GL of V if you want, a 2-dimensional vector space. And well, I don't really want it to write it that way, in fact. It's going to be a Galois representation which factorizes through a finite extension of Q. Okay, this is L, but it's not necessarily the same L than this one. It's just a number field. And so this is going to be G. And you go into GL of V. And what is V? So that's going to be a two-dimensional representation, which has certain properties, which should be irreducible. Odd. The meaning of odd is that if you look at the image of complex conjugation, the determinant should be -1. Yes, a Galois representation as a conductor. And also it has a sort of a ring of coefficients. R, which is going to be a subring of the ring of algebraic integers. You can see that in C if you want. Okay, so that's one type of object, and in particular, when you consider this object, you can certainly send S3, find the representation of S3 into a two-dimensional representation, and you get an object of this type. Okay, and so that corresponds to G. Okay, is it G or F?
It's a complex representation, right?
No, it doesn't have to be. It's a complex representation if you embed that bar into C if you want. But actually, it's as a representation, so it's with value in number it has coefficient in a certain number field, and actually even coefficient in the integers of that number field, which is that ring R. Okay, so on the other hand, you can consider a modular form. So this is a modular form of weight 1 for the group gamma 1 of n. So, and it's even a new form with coefficient in R. Namely the AM are in the ring R. So there is a bijective correspondence between these two sorts of objects. In that direction, it's due to Deligne and Serre, and the other direction, by a number of people, there is Hecke, Langland, Tunnel, Bozard-Taylor, and finally Carré, Vinton-Berger, who actually proved really it was a long-standing conjecture that you have actually bijective correspondence, and the bijective correspondence has to satisfy something, namely there is a numerical AP for P prime, not dividing M. AP is the trace of rho, and you take a Frobenius element at P, take which is well defined up to conjugate C. So rho from P is well defined up to conjugate C, but the trace is well defined. So it's really a number which belongs to R. And you've got this identity for all P's. So that's a general setting. And this is a setting that I will keep for the rest of the talk. So as I said, the conjecture of Harris and Venkatesh goes beyond simply this equality for every prime number P. There is something more actually than that rho and G share, and rho and G share more. Okay, so there are many entry points into that field. The conjecture of Harris and Venkatesh is a part of a very general conjectures Venkatesh, and this is a sort of the simplest case actually where the conjecture says something non-trivial perhaps, and there is this notion of derived Hecke algebra, in a sense. The conjecture of Harris and Venkatesh might be seen as a derived version of this bijective correspondence. But the word derived is a bit overused these days in mathematics. But nevertheless, you will have an infinite list of numerical coincidences, and so they share a collection of elements in what? In FQ star tensor R for Q prime number. Okay, maybe I will have to suppose that Q does not divide M, perhaps. Okay, so the goal now is to define those two elements from the point of view of rho on one side and from the point of view of G on the other side, and to state how they are related. There is a piece of notation. So to designate an element here, so if I take A in FQ star, and if I take R in R, of course you have the tensor product, and this will be denoted by A to the R, owing to the fact that FQ star is a multiplicative group. There is one thing I should say also. So we had in Paris this year a working group on the Venkatesh conjecture, and in particular we focused a lot on the Harris-Venkatesh conjecture. And what I'm going to explain, and which is really new, is a joint work with Emmanuel Lecouturier. But most of my talk will be about explaining the conjecture. Okay, so there are two sides. Let me call this the Galois side. And the other side. Is the automorphic side. or modular side if you prefer. So I need to define this element on the Galois side first, and that's fairly easy. So you have a representation of you have the representation rho, and you can attach to it the adjoint representation. So Galois side. So consider rho, the adjoint of rho. Which goes into the adjoint of V. So this is just an action by conjugacy, namely, which is a map which to, let me see, I want to write this, which to sigma associates a map which to adjoint representation. I can write it as, let's say, theta, sigma of G, theta, sigma of G, minus 1. Okay, so inside there is a sub-representation, which is the trace zero part. And which is, so the trace zero part, joint of V, trace, equal to 0. Okay. And so now there is the object introduced by Venkatesh, which is, okay, Michael Harris has a notation for this. I'm not sure it's appropriate, but he uses a Sanskrit letter Va for Venkatesh. That's his ID. In any case, okay, let me tell me if I write it correctly. Is that Va, correct? Okay. So, but what is important is what does this object designate? Okay, you look at the homomorphism from at 0 of V towards OL. Recall that L is a field through which this representation factorizes. So it's a number field, and you can consider its units. And also you have to extend the scalars by the ring R. Okay, and so now what is this thing? Actually, it's not that difficult to determine, and it's sort of so it's certainly an R module. And it's generically of rank 1, namely if you make a vector space out of it by tensorizing by Q. So R transcend Q is a field, and it's a field of dimension 1. So it's of rank 1. It's not hard to see. The only tool you need to prove that is a unit theorem, because the unit theorem tells you the structure of the units as a Galois module, and you have to be careful that the homomorphism have to be compatible with the action of Galois. Now consider an element phi into this var. And to phi, I will, for every prime number Q, I will associate an element in FQ star tensor R. Okay, so let Q be a prime number. Then Q0, a prime of L above Q, And then what do I need? Yes, and there is a Frobenius at Q0, which is well defined, which belongs to G. Yes, and belongs actually even to the decomposition group at Q0, containing G. And then you can consider rho of the Frobenius at Q0. So it's an element of the adjoint of V, but it's not necessarily of trace 0, so you have to you can project it on the trace 0 part. And to do that, you consider, so projecting on the trace 0 part is doing the following thing. Okay, so that belongs to the trace 0 part of V. Okay, so then to that, you can, now if you have an element here, you can consider its image by phi. And then you get an element in OL star tensor R by definition of phi. And that element, you can reduce it mod Q0. Okay, so then you get an element that I'm going to denote by RQ of phi. So this is a priori a finite field, which is a finite extension of FQ. But since phi is compatible with the action of G, and in particular compatible with the decomposition group, what you get is belongs in fact to FQ star tensor R. So it's a sort of a regulator of phi. Okay, so that's all for the Galois side. So we have made one choice, which is a choice of phi, and now you can let the prime number Q vary, but you have a collection of elements in FQ star tensor R. Now, so this is sort of not natural, but what needs to be done on the automorphic side is stranger. I mean, it took me years before I could really understand what is going on. So the game now is to start from this modular form G and to define the collection of elements in FQ star tensor R. Yeah. Okay, so then you have also a prime number, Q. So recall that we have a modular form G is sum of M Q to the M from equal 1 to infinity. And GQ bar is a modular form where you conjugate the coefficients. And I'm going to put a Q here because I want to make, this is still a new form, but now I want to make an old form out of it. So, okay, I have two Qs. Okay, Qs with a bar, Q like this. And this is a modular form for still of weight 1 for gamma 1 of M intersected with gamma naught of Q. And now comes the weird manipulation. So now you set GQ, which is, you take the product of G and GQ bar, and that's a modular form.
It's no longer the new form we're starting with. G is not a new form.
G is a new form. Is a new form attached to the representation.
But then A bar is equal to A, real algebraic. The bar is complex.
No, it can be, yeah.
It is a new form. Is it in the new form space or is it a new form?
G is a new form.
So then its coefficients are real algebraic.
No, because we are in the weight 1 case. You take the product of the two, you get a modular form of weight 2 for the intersection of those two groups. And now I take the trace from that group to the smaller group. So if I take the trace, I should go to gamma 1 of M intersected with gamma naught of Q to gamma naught of Q. And so I have taken the trace of modular form of weight 2. It's still of weight 2. So this is a modular form of weight 2 for gamma naught of Q. Okay, so I have this modular forms of weight 2. It's this capital GQ is not anymore a new form because by taking products you completely destroy you destroy the Hecke structure. So not a new form. Okay, so now I'm going to use a result that which is implicitly in Mazur's Eisenstein ideal paper, Mazur, and perhaps I should name Jesse Silliman, who seem to have written this explicitly. There exists a certain map, SQ, from the space of modular form from weight 2 for gamma naught of Q towards okay, so those are the modular forms with integral coefficients. So I'm going to put a Z here. So it's not a complex vector space, but modular form whose Q expansions are made of coefficients in the integers. And U12 is a set of roots, 12th root of unity. Okay, see if among you there are people familiar with the Eisenstein ideal paper of Mazur, you might recall that 12th root of unity play an important role. So this is essentially taken from the Eisenstein ideal theory. Harris and Venkatesh consider this thing from a different point of view, and they involve what they call the Shimura class. I told you there are many entry points into this business. In any case, there is a simpler way to describe this map than what Harris and Venkatesh did, and this is what I'm going to do now. So define as follows. You consider the space of modular forms, the full space of modular forms, not just the cusp forms, but the space of holomorphic modular forms with integral coefficients still, except that I want to write gamma 1 here. And you have a trace map which goes into M2 of gamma naught of Q. And here you have an action of diamond operators. This factorizes through plus or minus 1. And this map is surjective. In general. And inside this, you have S2, space of cusp form, still with integral coefficients. Which is not surjective. So we need to define this map, capital SQ. And so we start from a certain modular form, let's say, call it G. And we want to define SQ of G. So by this diagram, G does not necessarily have an antecedent here, but it might have it has an antecedent here. So equal trace of G1 with G1 in M2. So G1 has a Q expansion. Which starts at 0, in fact, Q to the M. So B0 is a constant coefficient. And then you can do the following, thing. Then SQ of G is the product for T running through the diamond operators. So diamond operator of what? Of T to the power of B naught of T G1. Okay, so the diamond operator T acts on G1, and you look at the constant coefficient of T of G1, so you get a number, and you take the products over all T's of this thing, and you get this map. So you might wonder why I had to divide up by the 12th root of unity. Well, there is a it's not something over which I want to elaborate, but let me say that there are certain modular forms in characteristic 2 and 3 for gamma naught of Q which don't come from characteristic 0. So it has to do with that. In any case, I'm now ready to state the conjecture of Harris and Venkatesh. Yes, okay, I forgot to say something. And in particular, our form GQ here does not have integral coefficient. It has coefficient in the ring R. So it belongs to S2 gamma naught of Q tensor R. And therefore, its image by SQ belongs to FQ star modulo the 12th root of unity tensor R. Okay, so now here is the conjecture. OK. So there exists lambda in R such that so it does not postulate really the equality of the numbers we have defined on both sides. It's a conjecture of proportionality such that RQ of phi is equal to SQ of GQ to the power of lambda. And for all prime number Q. So lambda is independent of Q. Okay, the question of 12th root of unity is completely irrelevant because you can just multiply lambda by 12, and so you kill the 12th root of unity. I have now a set of remarks and results actually on these conjectures. The first result might be due to Harris and Venkatesh themselves, namely that if SQ is equal to 0, so the automorphic invariant, then so is RQ. But the most substantial results concern a certain class of representations, namely the class which are dihedral. So you see, you have your you have a representation with value essentially in GL2 of C. You can look at the projective image, which is a projective subgroup. It's a subgroup of PGL2 of C. And the subgroup of PGL2 of C are all several types. And there are the abelian ones, but next to the abelian ones, there are the dihedral ones. And the main results so far concern the dihedral case. So so substantial results. And rho is dihedral. Namely, so the conjecture is proved with restrictions by Harris, Darmon, Roger, I should have said Darmon, Harris, Roger, and Venkatesh, so with some restrictions. Which are technical, I'm not going to describe. And afterwards, there has been another proof, which is due to Le Couturier. Different restrictions. And Le Couturier's proof is based on a different principle. It's quite elaborate, actually, to prove the conjectures. There is no direct way. And people used very involved techniques in automorphic forms to show that. And there is a third noticeable author, which is Robin Zhang, a student of Michael Harris, which actually improved on the four authors. And also, Zhang has formulated a more general, a slightly more general conjecture, which integrates the Harris-Venkatesh conjecture with Stark's conjecture.
Excuse me, can you recall the definition of RQ phi?
I'm sorry?
The definition of the left-hand side, the RQ phi.
Yes.
What was that?
RQ phi?
What was the definition of RQ?
This was the definition on the Galois side, which I have erased now. You see, you had to. It depends on phi, which is an element you choose in the VAR, but it's well defined up to a scalar in any case. So it means that since it is well defined up to a scalar, it doesn't matter that much for the conjecture because you have a power here, and so. Okay. Do I have time to say something about the philosophy of this? Okay, let's see that. Yes, so why does this concern particularly forms of weight 1? Harris and Venkatesh explains this, and it's in the context of the general conjecture of Venkatesh. There is a general philosophy, but it's connected to the fact that the L function, let's say, of the adjoint of GS has a simple pole at S equal 1, which is related to the fact that this R module VAR is of rank 1, so that's compatible with that. And that's a phenomenon which is particular to the weight 1. Okay, so then there are several interpretations of this SQ of GQ. This is a derived Hecke eigenvalue in the sense of Venkatesh. I should rather say pseudo eigenvalue because you've got sort of a Hecke operator which goes from the space of weight 1 form to its dual tensorized by FQ star. So it's not an endomorphism, but you have still a concept of a pseudo eigenvalue because you know an eigenvector on one side, an eigenvector on the other side. And so you've got a pseudo eigenvalue, which is SQ of GQ. This is one way of seeing that, and Venkatesh, once again, has a general philosophy for that. There is another philosophy which has been put forward by Zhang, which is to say that this is the analog. So recall that we started from a modular form of weight 1. And certainly, we can consider its Peterson scalar product, which is a complex number. But in that case, you can see this thing as the analog of the Peterson scalar product in FQ star tensor. So this is Zhang's philosophy. Okay, so 5. Zhang integrates Harris Venkatesh with Stark conjecture. Stark's conjecture. So Stark's conjecture is about, namely, the value of this L function at S equals 0. Or S equals 1, same thing by functional equation. So this is an Archimedean conjecture, and Harris Venkatesh is non-Archimedean, but Zhang managed to put them into under the same roof. And if you look at what the philosophy of, if you look at Harris and Venkatesh paper, it doesn't seem to make much sense, but except if you have in mind the notion of a triple L function. So what is behind? So you see here you have a sort of a double L function. So this is like the L function of f of G tensor itself, and you might want to add a third modular form, which is the Eisenstein series of weight 2 for gamma naught of Q. And if you look at this, the L function of this triple product at S equal, let me see, S equal 1, then you get this number as a sort of a factor. But I'm not going to be more precise than that. So since I have a few minutes, yes, I have more than 10 minutes, which should be enough. I'm going to tell you something about another way, still another way to consider those things, and which in particular provides a manner to compute this number on the modular side, on the automorphic side. And it involves so this is one thing I've done with Le Couturier. So I can only tell you today a fraction of what we have done so far, in fact. So because we are in the process of writing things, but I can tell you that. So it involves the theory of Borisov and Gunnels. So I have to write a diagram for this. Okay, so first you consider Z bracket SL2 of Z modulo gamma 1 of Q. That you can identify with Z bracket FQ square minus 0, 0 modulo plus or minus 1 by the following rule. To the matrix A, B, C, D, you associate bracket C, D, mod Q. So plus or minus gamma 1 of Q. Okay, so now you have a map from this to, so I'm going to consider the modular curve x1 of Q. Z, and the map associates to a matrix A, B, C, D. It associates the modular symbol G0, G infinity. Okay, so you have to picture the upper half plane. So G0 to G infinity. So G0 is going to be B over D. And this is going to be A over C. So you get an homology class which is not closed, but which goes from a cusp to another cusp. So it defines this, an element which is well defined here. And inside that group, you have H1, the absolute homology group, Z, and which is of course contained, and it's the surjective image of H1 of Y1 of Q. The Y1 of Q is a modular curve deprived of its cusp. So if you have an homology class, you can push it here, and this is surjective. Okay, and now, so yes, I need to have a name for this, psi1. This is, oh yes, there is a theorem of Manin which tells you that this is surjective. Okay, now I take a class here, X, and I associate to that a certain Q expansion. So there is a constant plus sum from m equal 1 to infinity of Tm. This is the mth Hecke operator. Tmx belongs to that homology group, but that homology group is dual to this one, and the duality is provided by intersection products. So what you have here is an integer. So you have a Q expansion, and this Q expansion is the Q expansion of a modular form. Gamma 1. Okay, but it's not exactly what I want to do. What I want to do is taking the image modulo Eisenstein series. Gamma 1, I'm sorry. Eisenstein series. And this is precisely the Borisov-Gunnel map. So this map, okay, so I have to, so you see, if you take an element, let me see. Yes, I take an element here, I can lift it here, and if I lift it here, I get a certain modular form. But, and then I can project into the space of modular form modulo Eisenstein series. And the result in that quotient space does not depend on the lift. So you've got this Borisov-Gunnel map. This is how it is defined. Okay, 5 minutes. Now. And Borisov and Gunnels prove a number of things. No, one else. First is that the image of BG is spanned by the new form F in S2 gamma 1 of Q whose L function does not vanish at 1. Okay, that's one thing. And the second thing is they actually compute. You see, you have special elements, image of, so you have this group which has a basis, and you can look at the image of the element of the basis by psi1, and you get element here, and you might wonder what is the image of those elements in that space. And so they provide an answer to this. So Bg of sum over uv in fq star minus 0 modulo plus or minus 1 of lambda uv psi 1 of uv. This is sum over the same uv of lambda uv EU EV. EU EV are Eisenstein series of weight 1, where EU is equal to, so this is the Eisenstein series whose constant coefficient is B1 bar U over Q. So this is an Eisenstein series. And okay, so this is a complete statement. Now you have a sort of an explicit formula for the map which goes from here to the space of modular forms, modulo Eisenstein series of weight 2, of course. And this Eisenstein series of weight 1. And here we have the product of two modular forms of weight 1. It is of weight 2. So this is reasonable. And there is now another Eisenstein series which has to be involved. So for W in FQ star modulo plus or minus 1, right? FW is also an Eisenstein series, but of weight 2 this time. And the constant coefficient has to be B2 bar of W over Q plus Q expansion. This is an Eisenstein series of weight 2. B1 bar and B2 bar are the Bernoulli polynomials made periodic. And now I can finish by stating a theorem about the use of Borisov gunnels for Harris Venkatesh. So you write, so GQ is this modular form of weight 2 that we had. You write it as, you can write it actually, this is not trivial, but you can. EU EV plus okay, so you write it as a sum, of product of Eisenstein series of weight 1 plus an Eisenstein linear combination of Eisenstein series of weight 2 with lambda UV mu W. Okay, I'm going to write that with the coefficient in R, and I'm going to remove 1/6 for certain reasons. Then Yes, and I want the lambda to be homogeneous for T in FQ star. Then SQ of GQ is the product of two things. Prod T of T UV of lambda UV B1 bar of TU. I'm just now applying the recipe I gave you for the calculation of GQ to this. TV over Q. Okay, that's one factor corresponding to this first term, and there is another factor corresponding to the other term times U to the power of sum over W of mu W. And what is U? It's something that I've computed long ago, but you can write it that way. Of T to the power 1/4 of B2 bar T over Q. And so all this belongs to R bracket 1/6 tensor FQ star. Okay, this factor you can understand, if you like, as the analog in FQ star of zeta prime of -1. So the derivative of the zeta function at -1. Okay, so that's our way actually to understand at this moment those objects defined by Harris and Venkatesh. Thank you very much.
Is there any questions or comments?
Yeah, so you got the L function at naught rho S on the Galois side, right? L of at naught rho S.
Yes.
So what is the corresponding thing on the automorphism?
Yeah. Of course, you can. You can define the adjoint of a modular form. So you've got this modular form G that you can write as sum of an q to the n, and now you can have the double Dirichlet series an. I think that's something like this bar divided by n to the s. So that's the L function of the adjoint of G and the adjoint of rho, but it has a simple pole at s equal 1. And you can see that it's not very difficult actually, simply because you can write that AP is. Okay, so I don't have the exact mechanism in head, but you can do it.
Just the Rankine-Selberg.
Yes, exactly. This is Rankine. This is.
Selberg will have a pole.
Yeah, that's right. But because of the weight one.
Okay.
Because of the weight one. And in weight higher than 1, there wouldn't be any pole. You wouldn't have derived Hecke operators, and Venkatesh theory would not tell you anything. So it says, this is really special to the weight one. Yeah.
Any more questions? You said you have some more results about.
Yes, but for this moment, I prefer not to talk about them.